mystery is occurring in today's office buildings and manufacturing plants. Transformers and neutral and phase conductors are overheating. Circuit breakers are tripping, and motors are burning out for no apparent reason. Yet the standard troubleshooting tools and procedures show everything to be normal. So what's the problem? Finding the problem is relatively easy once you have the right tools and know what to look for and where. This program will help give you a basic understanding of power system current harmonics. It includes some pointers on how to identify harmonics, as well as some methods to address the problem. You can also refer to the Fluke application note, which provides more detailed information. Harmonics are frequencies that are integer or whole number multiples of a fundamental frequency. If you strum an instrument in the middle, the strings vibrate at the fundamental or lowest frequency. If you strum near the bridge, the strings vibrate at the fundamental as well as at one or more harmonic frequencies simultaneously. In this way, the fundamental combines with harmonic sine waves to form non-sinusoidal or distorted repetitive wave shapes. In power systems, harmonic currents or voltages are multiples of a fundamental frequency. They're present in the distorted waveforms created by nonlinear loads. To understand, let's first look at linear loads. Under normal conditions, the voltage waveform supplied by an electrical utility will be a sine wave at the fundamental frequency. When a linear load is connected to a sine wave voltage, the current will always be a sine wave at the same frequency. In other words, a linear load does not produce distorted current when connected to a sine wave voltage. When the load contains nonlinear elements, the circuit may draw current in abrupt pulses rather than in a smooth manner. These pulses form a distorted current wave shape which contains harmonics. Harmonics are prevalent wherever there are large numbers of nonlinear loads, such as personal computers, lights with electronic ballasts, electronic office machines, and adjustable speed motor drives. Equipment that typically contains a switching power supply that has a nonlinear diode capacitor input circuit. This type of circuit converts AC voltage to DC to charge a large capacitor to the peak of the line voltage. The equipment then draws DC current from this capacitor to power the rest of the circuit. As the voltage goes through a complete cycle, the circuit draws short pulses of current only during the peak of the line voltage. This causes the current to become distorted, and it's this distortion which contains harmonics. This load can be represented by a resistor in parallel with several current generators operating at harmonic frequencies. The resistor conducts current at the fundamental frequency. The harmonic current generators pump out current at higher frequencies. These all add together to form the distorted current drawn by the nonlinear load, which enters the power distribution system where the load is connected to the power line. Each harmonic has a name, frequency, and sequence. In AC power distribution systems, the positive and negative portion of the current and voltage waveforms are nearly equal, so no DC component is present. Under these conditions, the even-numbered harmonics will not be generated. The remaining harmonics occur in three sequences in terms of the effect of their phasor rotation. The higher the frequency, the faster the magnetic field rotates. The positive sequence harmonics, including the fundamental frequency, are forward rotating. In other words, when applied to a three-phase induction motor, the rotor will rotate in the forward direction. The magnetic field produced by a negative sequence harmonic tends to cancel the field produced by the fundamental and rotates in the reverse direction. This effect can cause three-phase induction motors to burn out. And zero-sequence harmonics, known as triplets, don't rotate. Instead, they add in the neutral of a three-phase, four-wire system. Most of the harmonic current found in the neutral is due to the third harmonic. The effects of harmonics show up in the power distribution equipment that serves both the single-phase and three-phase nonlinear loads. Single-phase nonlinear loads are typically 120-volt receptacle and lighting loads found in offices and commercial buildings, while three-phase nonlinear loads are usually found in industrial plants where there are large motors with adjustable speed drives. Harmonics from single-phase nonlinear loads enter the system through receptacles and then cause heating in phase and neutral conductors and bus bars. At the load center, harmonics can cause premature circuit breaker tripping due to heat and frequencies greater than the 60 Hz rating. Shared neutral conductors in a three-phase system can be severely affected by nonlinear loads connected to the 120-volt branch circuits. Under normal conditions, for a balanced linear load, the fundamental 60 Hz portion of the phase current will cancel in a shared neutral conductor. However, triplet harmonic currents add together rather than cancel in a shared neutral, which results in neutral current that can be greater than the phase current, even if the loads on the phase conductors are balanced. This neutral current can typically be 130% of the total current measured in any individual phase. This situation is worse if neutrals are downsized. Again, the danger is overheating because there's no circuit breaker to limit the current in the neutral conductor. Excessive current in the neutral conductor can also cause higher than normal voltage drops between neutral and ground at outlets. Neutral bus bars and connecting lugs are sized to carry the full value of the rated phase current, but they can become overloaded when triplet harmonics add in the neutral conductors. Commercial buildings commonly have a 208 120-volt transformer in a delta Y configuration, which feeds receptacles in the building. When triplet harmonic currents in the neutral reach the transformer secondary, they're reflected into the delta primary winding, where they circulate and cause overheating and transformer failures. The same type of problems occur in single-phase systems with lighting loads at 277 volts. Harmonics are easier to detect if you have the right tools. This includes a true RMS meter that can capture an instantaneous peak reading in 1 millisecond to capture the half-cycle peak of the current waveform. The meter should be specified to a crest factor capability of at least 3, and it should have the ability to measure the frequency of the current. The term RMS relates directly to the heat harmonics produce in components of the power distribution system. If a distorted wave shape and a pure sine wave shape produce the same amount of heat in a resistive load, then the two wave shapes have the same RMS value. The word true in true RMS comes from the fact that not all instruments give correct readings for distorted waveforms. Most low-cost portable instruments are average responding, RMS calibrated, which means they give correct readings only for sine waves and typically read low when the waveform is distorted. Whereas instruments equipped with true RMS converters will give correct readings for any wave shape within the meter's crest factor and bandwidth limitations. A true RMS meter's crest factor spec relates to the level of peaking that can be measured without errors. The crest factor of a waveform is the ratio of the peak value to the RMS value. For a sine wave, the crest factor is 1.414. A good quality meter has a crest factor rating of at least 3 at full scale, more than adequate for most power distribution measurements. Once you have the right tools, a location survey will help you find out whether or not you have a harmonics problem and where it's located. Walk through the building. Look for personal computers and printers, adjustable speed motors, solid-state heater controls and dimmers, and fluorescent lighting fixtures equipped with electronic ballasts. If this type of equipment is present, chances are the electrical system contains harmonics. The next step is to locate the transformers feeding those nonlinear loads and check for excessive heating. Also, make sure the transformer cooling vents are unobstructed. Using a true RMS meter, measure the current in each phase and in the neutral of the transformer secondary. If it's a 4-wire system, compare the current measured in the neutral to the current estimated from the imbalance in the phase conductors. The neutral current would normally be 0 if the phase currents are equal in both amplitude and phase. If the neutral current is unexpectedly high, triplet harmonics are probably present. Next, measure the frequency of the neutral. If you're getting a reading of 180 Hz, the neutral current consists mostly of third harmonic. Compare the phase current readings to the rated current calculated from the nameplate kVA. For a linear load, the measured reading should not be higher than this value calculated from the nameplate. Survey the subpanels that feed harmonic loads. Measure the current in each branch neutral and compare the measured value to the rated capacity for the wire size used. Check the neutral bus bar and feeder connections for heating or discoloration. Also measure the current and frequency of all the neutrals. Again, 180 Hz indicates the presence of third harmonic. To detect overloading in receptacle branch circuits, measure the neutral to ground voltage when the loads are on. 2 volts or less is probably normal. Higher voltages can indicate trouble depending on the length of the run and the quality of connections. Once you've followed these steps to locate where harmonics are occurring, you can begin to solve the problem. One way to protect a transformer from overheating is to derate or limit the amount of load placed on it. The NCI-EEE derating method is the most rigorous and can be applied to either 3-phase or single-phase loads, and requires loss data from the transformer manufacturer as well as data from a harmonic analyzer. For the special case of office buildings with typically single-phase 120-volt receptacle loads, there's an alternative method established by the Computer and Business Equipment Manufacturing Association. This CBMA derating method should only be used for single-phase loads. Measure the peak and true RMS current values for each of the phase conductors. If the phases are not balanced, average the 3 and insert the average value. This formula generates a derating factor value between 0 and 1, typically between 0.5 and 0.9. A value of 1 indicates no harmonics are present, so no derating is required. As the peak of the phase current increases, the derating factor value diminishes, which means the transformer must be derated. The transformer derating for a harmonic load is the product of the nameplate kVA rating times the harmonic derating factor. For example, let's look at a 208 120Y transformer rated at 225 kVA, feeding receptacles in an office building. The true RMS phase current values averaged over 3 phases is 430 amps. The peak phase current values averaged over 3 phases is 841 amps. Using the CBMA formula, the calculated derating factor is 0.723, indicating the transformer should be derated to 72.3% of its nameplate rating. There are a number of steps that can be taken to minimize harmonic problems in the design of new facilities. First, using a true RMS meter, determine what the actual load currents will be for specific types of equipment. Then, wherever possible, design for this known load current. Reduce the number of receptacles per circuit to allow for the extra voltage drops caused by harmonics. Pull extra neutrals in branch circuits or use oversized neutrals. Use oversized feeder conductors and conduit for better heat dissipation. And also oversized load centers so that bus bars will not be overloaded. Or use load centers rated for nonlinear loads. Specify harmonic rated circuit breakers in the design. require a harmonic-rated transformer with a K-factor appropriate for the load. Arrange branch circuits and feeders so that three-phase induction motors are not connected to circuits serving nonlinear loads. Wherever necessary, use isolation transformers. And specify that the people doing maintenance on the system be equipped with true RMS measuring instruments. Fluke offers 3 high-performance meters with true RMS capabilities. The Fluke 87 handheld multimeter measures true RMS voltage and current with a crest factor of 3. The 87 also features frequency, peak, and min-max measurements. To complement the 87, for harmonic applications we recommend the 80i400 and 80i600 AC current probes. The Fluke 30 series Current Master clamp meters provide true RMS measurements of current up to 700 amps and also measure the frequency of neutrals and adjustable speed drives. The Fluke 33 features crest measurement for instantaneous peak current as well as min-max for inrush current up to 1000 amps. Reliable, accurate Fluke tools designed for the professional electrician to help take the mystery out of harmonics. Call for a harmonics application note or for more information.